Hello, I would like to talk about the small tectonic displacement mapping from SAR offset using the time series analysis for the noise reduction and its uncertainty quantification. We know that SAR can measure the distance between the radar antenna and ground surface through INSAR using its phase information or through pixel tracking or speckle tracking using its amplitude information. Here we refer to as offset. For both of them, the range change can include several components, including the orbit, the tropospheric delay and ionospheric delay, and Earth motions. For Earth motion specifically, it includes the displacement from tectonic and other processes, which has a wide range of variability, and other tidal and loading effects. Among them, the largest one are the solid Earth tide, which can be up to plus and minus 20 centimeters. Traditionally, SAR offset, estimated from speckle tracking or pixel tracking, has been used to map the fast displacement processes in meter scales, such as the ice velocities in Greenland and Antarctica, the cold seismic deformation from large earthquakes. However, with the availability of the long time series from Sentinel-1 and the GPU-based technique to speed up the cross-correlation process by over 100 to 1,000 times compared with the CPU-based version, we start to wonder that can we use SAR offset to measure the small displacement in millimeter or centimeter scale or not. Compared with INSAR, speckle tracking has a few advantages. First, it does not require phase unwrapping, which is computationally expensive and error-prone. Second, it's a especially absolute measure, which means there's no need for reference point in space, making it easier to mosaic and scalable for large-scale processing. Both of these will make the workflow of offset much simpler than INSAR. The disadvantage is offset usually has low precisions compared with INSAR with also relatively low spatial resolution. Here we take the Southern California as test site, where we know from INSAR that there is a 1.5 centimeter per year of interseismic deformation in the radar line of sight directions. And the question here is, can we use the SAR range offset to measure this small displacement or not? Theoretically, the standard deviation of offset estimated through incoherent speckle tracking can be described as a function of the cross-correlation estimation window size n and the spectral coherence gamma, and plotted on the right, where different color represents different chip size for the estimation n. Given a spectral coherence of 0.6, the standard deviation can already give us, for most of the current satellites, a standard deviation of 1 centimeter or less, which is already a fraction of the wavelengths. For time series analysis, we can generate a stack of the offset and propagate this uncertainty through the time series to the velocity domain and plot it on the right, where the left is just a standard deviation of the equation for the linear propagation of errors. On the right, the x-axis are the length of the time series in years, while the y-axis are the standard deviation of the offset velocities. Here we use Sentinel-1, the range offset, as a reference. Assuming a 12 days repeat time, we consider a temporal decorrelation model with an exponential decay, giving a time series of 5 and 5 years long with a network of 10 connections. The standard deviation could already reach to 1.2 millimeter per year, which is promising. So we go ahead and process the real data. We choose a Sentinel-1 descending track at Southern California. It's 5 and 5 years long with over 170 acquisitions corrected using pure geometry. We then generate a stack of offset with sequential networks using its 5 nearest connections to generate over 800 pairs. We then run the small baseline time series analysis approach to the stack of offset, just like what we did for INSAR. Then in the time series domain, we correct for a few bias sources, one including the Sentinel-1 A and B range bias, the solid Earth tide using an open source package called PySolid, the tropospheric delay using ERA5, the ionospheric ramps using the GNSS-based tech products from the JPL Global Ionospheric Maps. This plot here shows the configuration of this network, where the dots represent one SAR image, one line represents one offset pairs, and the color of the line represents the averaged offset standard deviation. And the result looks like this. We can see that overall there's some spotty patterns everywhere. It's short wavelengths. It's a processing artifacts caused by the large estimation window size of the cross correlation and the median filter afterwards in the post-processing. But beyond that, we can see two signals very clearly. One is a large-scale interseismic deformation across these plate boundaries. Here is the Salton Sea for your reference. And if we plot a profile on this mean line of sight velocity and show it on the sea, we can actually see a very clear interseismic deformation rate across the San Jacinto Fault and San Andreas Fault with a magnitude of 1.5 centimeter per year, which is just what we expected. Besides that, we also see a large movement in the southeast across the US and Mexico boundary. This is a large displacement due to the movement of the sand dunes. To validate our observations, we compare the SAR offset velocity with the independent GNSS observation here, and these are plotted on the circles here on the top here, and we also plot the scatter plot in B. And we can see that generally there's a pretty good fine agreement between the SAR offset and the GNSS. The root mean square error between the two is around 6 millimeter per year with an R-square value of around 0.7. Here is a closer look to the displacement time series of the sand dune movement. It's huge, with over 2 meters per year of displacement rate, which is already beyond the detection limit of an INSAR. For the uncertainty quantification, we generate two versions of the standard deviations. On the left shows the standard deviation propagated through the time series, which represents the uncertainty of the offset or the cross correlation estimation itself. And on the right is the standard deviation from the linear fitting of the time series for the slope. It represents the uncertainty from the atmospheric delays, the nonlinear motions of the ground, and biases between Sentinel-1 subsources, and it's clearly much more dominant than the cross-correlation estimation itself. So in conclusion, yes, we can measure the slow tectonic displacement using SAR range offset, such as the 1.5 centimeter per year of interseismic displacement at Southern California, and this is because of the availability of the very long SAR time series images and the noise reductions through the cross-correlation with large estimation window size and the corrections of bias sources from solid earth tide and atmospheric delays. The source of the uncertainty in the SAR offset time series, including the offset estimation technique itself, the atmospheric delays, the uncompensated tidal effects such as ocean tidal loading. With the GPU-based SAR cross-correlation technique, scaling this algorithm to a large scale seems actually feasible and promising. For the future, we're working on more precise cross-correlation techniques such as the coherent version, especially for the Atmos offset, which has coarser spatial resolution and thus more challenging. And second, to improve the post-processing algorithms to better mask and filter the offset estimate, which has relatively low signal-to-noise ratio for applications of small displacement. Thank you.